Okay, on this lesson, I am going to address the big question that we saw on the worksheet from lesson number 8, which was, what do I do when my axis of revolution is not the X or the Y axis? Okay, so basically, kind of to summarize what we did all last week, I'm going to go through kind of the 4 cases that you're going to see when you're applying the disc and washer method. Okay, but basically, the big idea says, when using the disc and washer method to find the volume of a solid of revolution, the most critical thing is to determine how you're going to express the radii of each disc or each washer before you jump into creating your integral. So, if we go ahead and look at kind of case 1, okay, case 1 is the x-axis is the axis of revolution. And the function obviously has to be written in terms of x, so it's going to be in y equals form. Those functions need to define the radii. So if we look at an example, we're going to draw a lot of examples, so bear with me today. It's going to be tedious, but I think it'll be really helpful. And we have just one function. Let's start with one function. Okay, let's maybe call that f of x. And we are wanting to rotate f of x around the x-axis. Okay, so we can kind of picture that rotation occurring. But what is going to define the radius in this case? The radius, we draw in the rectangle that is perpendicular to the axis of revolution. Okay, so what is the height of that rectangle? The height of that rectangle, because it is drawn to the x-axis, is simply defined by whatever the function is. So if I am finding the volume of this solid of revolution, okay, I'm taking pi times the integral from a to b, and we are taking our function value at every given point between that interval, and we are squaring it. That is the radius. Okay, so that's kind of like the simplest problem, I would say. So the radius is defined by that vertical rectangle. Okay, but then the other case in this situation is we have our xy axis. We're still rotating around the x-axis. Okay, but now we have 2 functions, and we'll call maybe this first function is g or f of x. And then we have a second function that we can call g of x. Okay, but we are still going to be rotating around that x-axis. So if we kind of do somewhat of a mirror image, you guys are better at this than I am. Okay, that's kind of going to define the revolution. But before we write our interval, we have to think of big R and little r. Okay, big R is considered the outer function or the further away function, and little r is considered the inner function or the closer function to the axis of revolution. So you've got to draw the picture. There's really no way around it. You've got to graph it. Okay, now our axis of revolution is still the x-axis, so I'm looking at what's going to be the longer of the 2 rectangles when I kind of put them side by side. Well, the longer rectangle is going to rely on f of x. Okay, so big R in this case is my f of x. And then when I draw my radius of the inner function, that is drawn from g of x. So little r is my g of x. So now, okay, I find my limits of integration off the axis of revolution, or if the x values, okay? And so now I'm going to do my integral from a to b. Don't forget to stick pi out front because we're basing it off of pi r squared. And so now I'm going to take the function f squared, and I'm going to subtract the function g squared. Okay, and let me emphasize that this has to be written in terms of x's. Okay, so the normal functions that we are used to. So dx is tacked on at the end. Okay, so then you can kind of make your revolution occur and see that that's going to be the washer method, because you're going to take the volume of the purple and subtract the volume of the green to get a hole in the middle. Okay, now we're going to look at the y-axis being our axis of revolution. So that was kind of the second basic thing, I guess. But the big thing with, if we're using vertical axes of revolution, we have to have our functions written in terms of y. Okay, so our first example, let's just use the disk method. The disk method, I am going to go ahead and draw a function in. Remind myself that I'm rotating around the y-axis. Okay, so I can kind of mirror image that here in a second, but let's just call this f of y to remind ourselves it needs to be solved for x. It needs to be written in x equals form. Okay, and from here then, when I draw and think about the radius, I'm drawing it from my axis of revolution. Always go to your axis of revolution and think about, okay, what is the height of these rectangles in here? It's going to be defined by the value of the function when I plug y in, whatever I get out for x. Okay, so in the disk cases, there's only one r to worry about. So what is my integral going to be? It's going to be pi, okay, and then in this case, where do our limits come from? Okay, the y values. Everything has to do with y. So a to b of f of y quantity squared, because that is the only radius that we need for the problem. Okay. Now, moving on to the washer method, if we have two functions involved. So let's look at, maybe we have our first function as some sort of curve. We can call that f of y. And then maybe our second function, it can be anything we want, but maybe it's linear. And we can call that g of y. Okay, and then we are going to rotate around the y-axis, and we're going to think about then, if I draw in those rectangles, okay, the further rectangle, the outer rectangle, goes to the purple in this case. So we're going to say that big R is f of y. Okay, and little r, the closer, the shorter rectangle, when we go from our axis of revolution, is g of y. So we can envision kind of a hole in the middle when we reflect our two functions, like so. Okay, and you can see that like some sort of bowl is going to be made here. So what is our integral going to be? Integral, again, we look for our limits on the y-axis when we're written in terms of y. So we have pi from a to b off that y-axis, and we are going to take big R squared minus little r squared, so those exact function values after you solve for x, and you put parentheses around them and you can utilize your calculator. Okay, so most of you guys showed mastery last week of these two topics. Now, moving to the final two topics, this is where we're going to look at some examples and some more practice problems today. We are looking at first, okay, what if the horizontal line is the axis of revolution, but it's not the x-axis? Okay, we have to know what's our big R, what's our little r, but it's not just going to be the function. Okay, so let's look at two examples of this first. So we have our x and y axes. So you might want to label those. X and y. Okay, but let's say that our axis of revolution is up here at y equaling a, we'll call it. So that is what we are revolving around. And let's look at, maybe we have some sort of upside down parabola going on, and they tell us that they want this, okay, to be the function that is rotated about the line y equals a. Okay, great. So we can envision kind of what that's going to look like if I bring my arch up here, and we can draw in our circles to show the three-dimensional object. Okay, but it would be really tempting to just say we are going to take, let's call this f of x, and we are just going to integrate f of x. But if we draw in our rectangle from the axis of revolution, this rectangle is not the height of f of x. What is the height of f of x? You might not want to draw this in, but this blue rectangle is f of x right here. But that has nothing to do with the rotation. Okay, so what we have to think about is we have to use our knowledge of height and essentially know that the length of the red rectangle is related to the length A. Remember, A is a constant. And we have to subtract f of x, this little portion that I'm scribbling out of the black. If I scribble out the blue portion here, what is the black left with? It's the rectangle that is drawn from the axis of revolution to the function that we care about. Okay, so in this case, our radius, there's only one radius in this problem, it's a disk problem, is going to be expressed by taking a, that is a constant, and subtracting, and I'm going to put it in parentheses, our function f of x, because a lot of times a function has multiple terms. Okay, so this constant becomes part of the radius. So then what is our integral going to look like? Okay, our integral is going to go pi from, I'm going to use c and d, those come off still of your x-axis because that is horizontal. And we are going to be looking at a minus f of x quantity squared dx. Okay, so the radius has to go in brackets and you square it. Now, don't just memorize that it's always going to be the constant minus, because sometimes it might be the constant plus, and we'll see that here in a little bit. So you have to draw the picture and you have to think about what makes sense. Okay, some people don't like that because it's not as procedural as we're comfortable with. Okay, so now let's imagine that we have our x and our y, but we're again saying let's rotate around this axis, y equals a, and let's look at kind of a petal shape again. That's normally kind of what we turn to. So we have maybe kind of this parabolic shape first, and then we have the upside down or root shape here, and we are rotating it around our axis so we can envision kind of what it's going to look like, but we need to think about what's big R and what's little r. So big R is the function that is further away, which is the purple. But if I just say big R is f of x, that's not correct, and people are going to fall into that trap. Okay, what is big R? Big R is going to be a, okay, what's the distance of a? It's this whole distance here, and what do we want to subtract? We want to subtract the function because function values are found from the x-axis up, okay, and that's what we want to subtract. So then little r, once you figured that out, usually little r is going to follow the same pattern, but let me get my red. I'm going to draw in my little rectangle here, that's little r, and think about I still want to take a, but I'm going to subtract my green function, which maybe we'll call g of x. Okay, and that is what I'm going to integrate. Okay, so sorry, I'm kind of running out of room here. You organize better. But what is my integral going to be? My integral is going to be pi times the integral from c to d, and I'm going to take, let's see, a minus f of x, lots of parentheses, squared, minus a minus, I'm just going to write G quantity squared dx. Okay, so you've got to be careful when you type these into your calculator because there's a lot of room for error if you don't put certain things in parentheses. Okay, hang with me. We're on our last case now. Okay, so now we're looking at if the vertical line is x equals b, and that's not going to be the y-axis. So the first one that we'll look at is, let's look at the vertical line being to the left of the y-axis. So we have x equaling b is the equation of that vertical line. That's what we're revolving around. And maybe we have some sort of parabola going on here. Okay, so we can call that f of y. You would need to solve it in terms of x equals so that it's written in terms of y. But then let's think about, in this case, our rectangle. If we draw it from the axis of revolution, okay, if you say it is 1 minus f of y, that is not correct. Because what is f of y? F of y gives us this distance, but we also need this distance. So in this case, our radius is going to be, okay, this distance is b here, so we're going to take b plus f of y. So that's where I said a few minutes ago, you can't just memorize to always subtract. Okay, so once we've established that, you're looking at your limits of integration based on what the problem says, but they're off the y-axis. So we have pi from c to d of b plus f of y, and be careful with that f of y, put that in parentheses, or f of y in parentheses, whatever that function might be, square it. Okay, so then on the other hand though, if we look at another example, maybe I will put the axis of revolution on the opposite side in this case. So here we have x equaling b, and maybe our first function is a line. Maybe we have a linear function, and that is f of y. And then our second function that they're looking at is a parabola, and that's g of y. Okay, so then now we need to draw in our rectangles because we're thinking about rotating it, and it's going to be kind of like a TP type triangular shape when we rotate it around here. What's it going to be? Okay, it's going to look like this. Okay, but when we go back, we still need to define our radius. So if I go from the axis of revolution to the farther of the two, okay, I'm thinking about, well, the entire distance from the y-axis to x equals b is b. And what do I want to eliminate? I want to eliminate this portion right here, which is defined by f of y. So we're back to subtraction where big R is going to be, let's see here, b minus f of y. We've got to eliminate that little chunk there, and that will leave us with the red in the picture. And then same thing is going to go if I draw my rectangle to the purple graph from the axis of revolution. My little r is going to be the entire distance from the line all the way back to the y-axis, and I want to eliminate g of y, that little chunk that I'm scribbling right now. That's g of y. You always measure a function to the axis it belongs to. So now what am I going to do for my integral? Okay, I'm running out of room, so I'm just going to kind of highlight. I'm going to take the integral, and I'm going to take this value and square it, and I'm going to subtract then this value down here after I square it. Okay, now don't do any fancy algebra because your calculator is going to do the job at that point. So now we're going to do two examples of what we just talked about that I saw you're not as comfortable with, and that's understandable. We didn't focus on it last week, so we're going to focus on it now. Okay, so this next problem says, example 7, find the volume of the solid generated by revolving the region bound by the graphs of the equations we have our equations. X squared is y minus 2, and then we have 2y minus x minus 2 equals 0. And we see that also the region, some of you guys are kind of reading too fast on some of these. The region is started by x equals 0 and stopped by x equals 1. And our axis of revolution is y equals 3. And that's huge because we know y equals 3 is going to be horizontal. So immediately when I think horizontal, I know my functions need to be in normal y equals form. Are they in y equals form? No. So that might be the first thing that I'm going to do. Okay, so this first function here, I am going to move my 2, so I have y equals x squared plus 2, so we have a parabola. And then on this function, I have, maybe I'll go up here with it, I have 2y equals x plus 2, and then divide everything by 2, so I have y equals 1/2 x plus 1. Okay, so now we have our two functions that we are going to work with. So we definitely want to create somewhat of an accurate picture, so you need to use your graphing calculator to know which one's on top, which one's on bottom, and so on and so forth. So you might want to pause me and explore it on your graphing calculator. I did it before the video. Okay, so we have our linear function is going to be going like this, and then the parabola is actually going to be above it. Like this. And the axis of rotation, which is y equals 3, is going to be occurring above the parabola here. So this is y equals 3. And we are focusing from the line x equals 0 to x equals 1, which is about right here. So there's no intersection. Those are just going to be our limits of integration. Okay, so we are wanting to rotate this around the horizontal axis. So we need to think about our big R and our little r. Okay, so let's look at our big R first. Our big R is drawn from the axis of revolution to the further away function. So I'm thinking about what is the length of this. Okay, well, I know the length of this entire segment here is 3, and I know the length of this is defined by 1/2 x plus 1. So it's defined by a function. So what do I need to do? I need to eliminate this portion right here from 3. So I get 3 minus 1/2 x plus 1. Okay, now you can certainly distribute. Some people like to do that. Other people don't leave more room for mistakes than you need to do. So we have negative 1/2 x, and then 3 minus 1 is 2. Okay, and then we have to draw in another rectangle, but to the closer function. So if I draw that shorter rectangle in, we call that little r. And again, we are looking at the whole length being 3, but we have to subtract the entire quantity from the green parabola all the way down to the x-axis, which is defined by this right here, x squared plus 2. It has to all go in parentheses so that the negative distributes, okay? So now it's time to integrate. So when we set up our integral, we are going from, they told us in this case, okay, because there's no intersection points. If they don't tell you, go by the intersection points. So big R. Okay, I'm not going to use the condensed version. I'm going to use this version to show you that we need to rely on our calculators, okay, which is weird to hear a teacher say. And then subtract little r squared, and we have dx. Okay, so go ahead and pause me and take a minute and use the integrate feature. So you're plugging this entire thing into y1. y1 equals, and then you're going to second calculate option number 7, which says integrate, and then you're going to input 0 for the lower limit, 1 for the upper limit, okay, and when you press enter, you should get 2.55, okay, so we have to remember that there is a pi sitting out in front of that, so then when we you can just press times pi and it'll take you to your home screen, and you are going to get 8.01 units cubed as your answer. So I definitely want you to try this to make sure you know how to plug everything in correctly. Okay, so this is example that we have to do some fancier work on the radii. So the radii are not just always going to be the function, unfortunately. Okay, one more example. It says, let's look at the region in the first quadrant, okay, that is bound by the graphs. We have a cubic and we have a linear function, and we are revolving it around a whole vertical line. So when I see vertical line, I know I need it to be in x equals form. Okay, so if I look at this first function right away, I need to get my x by itself, so I have 8y equals x cubed, and then I cube root both sides, so I have to cube root the 8 to get 2, and then I'm going to write it as y to the 1/3 rather than the cube root, because I know I'm going to use my calculator here in a few. And then this one, we've got to divide by 2, so we get 1/2 y equals x. Okay, but I'm going to use the original functions to make my graph for sure. You've got to use a graphing calculator to get an accurate picture. Sorry. Okay, so I have my cubic function looking like this, and I have my linear function looking like this when I put it into a graphing calculator, and then my axis of revolution is -2. So then when I rotate, I'm going to have this shape going on with a giant hole in the middle there. Now, when I think about what my radii are, I'm drawing from the axis of revolution to the faraway function. And I know that this chunk right here is defined by the function because I go to the axis that it belongs to. So then what do I want to do? I need to add 2, not subtract 2. Even though it says -2, we're looking at absolute value here. We have to add this chunk. So our big R in this case is 2 plus, this is the further function, which is the cubic. So we have to add 2y to the 1/3. It has to be written in terms of y because we're using horizontal rectangles, perpendicular to the axis of revolution. Okay, and then for our little r, same idea. I'm drawing in my rectangle to the closer function and thinking about the little chunk to the y-axis is going to be defined by the function value, but I have to add 2 because I have to get backwards to the axis of revolution. So I have 1/2 y that I'm adding it to. So now I have to think about when I set up my integral. Okay, I'm looking at, because they didn't tell us, or we're looking at it bound, so we look at the point of intersection. Always know on your graphing calculator how to find this, but the point of intersection is 4, 8, so what number do we use? We have to use the number off of the y-axis in this case, and we can see that they can join at 0, 0. So I'm going to take 2 plus 2y to the 1/3. I don't have to use parentheses on that one because it's only one term. And then I am going to subtract my little r, the closer function, 2 plus 1/2 y dy. Okay, now when you use a graphing calculator, all the y's are going to be x's because they don't interchange there. So I want you to pick up your graphing calculator and use the integrate feature at this point. Again, we're beyond doing the integrals by hand. We're now worried about and concerned about setting up these different applications. So then from here, you are going to multiply. I think you get about, let's see, 66.13, and then you're going to multiply it by pi. So when you do that, you're going to get 207.76 units cubed. All right, so hopefully now you're feeling a little better about what happens when the axis of revolution is not the x or y axis. Your practice problems tonight are going to be over this concept, but please reach out to me if you're still having trouble. I'd love to help. Keep working hard, and we'll keep moving forward.